All right, good morning. So, yeah, I will take you guys' question. I just saw from the chat, some of you want to discuss maybe the written test questions. Yeah, can you tell me which one you want to look at?
Hey, Professor.
Hi.
I was just gonna ask about the, I think it was triangular sum.
Triangular sum, sure.
Yes.
Yeah, let me just go there first, and then we'll take a look. Just give me one moment. It doesn't matter which section it is. So, and then start a new preview, and then go here, and then finish. So we'll look at the answer and the question together. Okay, so you mentioned triangular sum, so it should be not here, of course, not here. Oh, triangular sum. Yes, over here. What about it?
So I think
Mm-hmm.
we in this task we were to um like find all of the primitive operations until execution.
Yeah,
Is that right?
yeah, that's correct. So you can think about, okay, for this one here, let me do a little bit annotation here, but of course, if you want to dive deeper, we can do that as well. Just give me one moment. I will just set it up on my iPad. Okay, so let me just take a screenshot over here. Okay, and then let me just paste that to my iPad. There we go. Okay, good. There we go. All right, so for this one here, if you look at the question itself, so we say that for each iteration of the outer loop, okay, so between line number 3 and 7, so here, basically we talk about this is the outer loop. We're talking about this one here. And then how many primitive operations are executed from line number 5 over here, okay? So we are saying that for each iteration, so for a particular value of I, basically, right? You can see over here, the I value could be from 0, 1, 2, all the way to the last value that's going to make this condition true will be n minus 1, because as soon as I gets to n less than n is going to be false. We are not really counting all the primitive operation added up together for each iteration. I mean, all the iterations. The question is asking just for each iteration, just for the particular one. So what you really got to look at would be basically this one over here. Okay, that's what you want to look at over here. Okay, so if you look at that one there, you can see if you look at here, for each iteration of the outer loop, you're going to run the inner loop, right? So this will be the inner, the one I'm highlighting in pink. So for that one there is going to be j is going to be from I, and then I plus 1 all the way to n minus 1. Okay, so and for each one of them, you're actually going to execute line number 5 for each one of them. And if you look at line number 5 over here, you're going to see this one you can rewrite it a little bit, right, just to make it a little bit clearer, more explicit. So sum equals sum plus a j. And if you just count that one there, this is 1 array indexing, and then arithmetic, and also variable assignment. So we got 3 in total. So every time you try to execute this line over here, you're going to get 3 primitive operations. So 3 primitive operations. So what you're going to do is you want to think about, for each value of the I, you're actually going to execute j from I until n minus 1. So you want to think about how many there are, right? So basically we're talking about the interval from I all the way until n minus 1. Okay, if you think about this one here, it's going to be n minus 1 minus I plus 1. So that's a little formula that we spoke about actually in the class, right? If you simplify this a little bit, it's going to be, of course, minus 1 plus 1 cancel out. You got n minus I. Okay, so we talk about n minus I iterations for the inner loop. for every value of I. Okay, and then we know that for every iteration of the inner loop, we're going to get 3 primitive operations. So we're going to multiply these two numbers together. So that'll be the answer. Should be. Does it make sense to you?
Yes. So just quick question. So we're supposed to multiply the number of operation in like the expression and then multiply with the amount of times it will get executed.
Yes, exactly. So I think usually when you want to solve this type of question here, you want to, it's usually like a multiplication of something by something. So usually, well, just in principle, of course, there might be some variance depending on the problem themselves. So usually for this type of question, there is going to be something multiplied by something. And usually the right-hand side, you can think about this one here is about the number of primitive operations for individual line. For example, here we talk about this particular line. So I count just for that line, there are 3 in this case. On the other hand, on the left-hand side here, it's about how many times you're going to execute it. And here, how many times over here could be just about a single loop, or it could be when we talk about the header of the loop. Together, in which case you have to enumerate about the like a triangular, like a shape, like what we said in the class. So I would say this part here is about the number of iterations. And for the number of iterations, you have to somehow look at the problem itself to see which one you're looking at.
Okay.
Okay.
Because I think I had a different version of the test.
Okay.
It was for specifically the I less than n. It was I less than n plus 1, and I did it myself, and I got a different answer from the solutions.
Right.
So what I thought was I less than n plus 1 was 2 operations, and that all in all was going to get executed n plus 2 times.
So sure. It sounds like you're talking about maybe a slightly different problem here. So because just for this one specifically, since we are talking about just line number 5 over here, so that's why I was only looking at this. But if you're also talking about, let's say, the one in the middle, let's say over here, let's say if you just talk about, let's say, j less than, for example, n plus 1, and of course for this one here, this will be 1, and also this will be 1 as well. So that'll be 2. And of course, that's going to be multiplied by, the number of times you're going to execute it.
Okay, thank you.
Yeah, no problem. Yeah, I think overall, I think for the exam, you guys may want to maybe go back to the example that we actually covered in the class. I think we definitely covered some like a single loop, and also we covered some nested loop. And also if you go back to the practice question, the practice question for both your written test and also for your exam, we also gave you some practice for nested loop. I think these are all nice examples there. I think the patterns are pretty similar among all the problems. So if you're given something similar in the exam, could be slightly more complicated, but I think the principle will be the same. So you just gotta make sure you kind of follow the principle, which will be, you want to look at which line you are focusing on specifically, and look at that line. For example, like this one here, right? Look at that line, first of all, just to see how many primitive operations are involved. And then you want to think about how many times you're actually going to execute it. And then how many times itself could be maybe just the inner loop, or it could be just the outer loop, or it could be the inner loop and outer loop combined, right? So we have seen examples, in different scenarios. So you want to judge. Okay. All right, so that's about the first question. Okay. All right, guys. Any other questions? Please go ahead.
Okay, I had a question.
Go ahead, please.
From the example questions that you've given us.
For the exam?
For the exam.
Yeah, sure. Let me just go there first. Sure, no problem. I'll go to the solution directly, so just in case. Yeah, sure. Which one?
Question 3, part B.
Question 3, part B. Let's take a look. Okay, sure.
Okay. I think it's just down to my own personal understanding of time complexities, but if let's say I had only guessed one of them, which I only guessed B as the one to be correct. Would that be okay, or would we have to guess all of them? Because
okay, yeah.
We immediately only clicked that B made sense to me and not the others.
Sure. Okay. So I think this question here, let me just give me one moment. Yeah, exactly. So the two keywords you want to pay attention to over here is about being correct and also being accurate, right? So when we say correct, let's say here, which for part B to, yeah, okay, let's take a look at here. So this one here is definitely correct, because if you look at the highest power here, it's actually 1, n to the power of 1. So in that way, the most accurate bound will just be big O of n. That one, obviously, I would choose that first as well, like you. However, if you look at, let's say this one here, this one obviously is wrong, because the highest power here is actually 1. But somehow this one here is like an n to the power of 0. So it's lower. So it's definitely wrong. It's not even correct. And let's look at this one here. This one is interesting. This one here, you can see D here, for example, is considered as correct. However, we didn't choose the D as an accurate bound, because the only one that's accurate is the big O itself is actually the same power as the highest power for the equation, right? So now, if you look at this one here is what we call correct but not accurate. In some ways, not very useful, because I'm saying, okay, my algorithm here could be, let's say, a linear search. That one is a linear search algorithm, but I'm saying the worst case, asymptotically, I can go up to exponential. Mathematically, that's correct, because you can easily choose a C to really choose a very small value of C, and then you can easily prove that this 2 to the power of n can upper bound 3n plus 7. So mathematically, D is actually correct. But that one is not very useful, because you just say in the worst case I can get to exponential, but practically you never get there, right? So I think it's really important to really see the difference between being correct and being accurate. So being correct is definitely the first step, but when you look at the same runtime function here, if you look at A here, let's see if I can select all of them. Okay, A, B, and then D, and also F, right? So you can see for the same function 3n plus 7, which is linear, the only thing that's both accurate and also correct, which would be useful, would be option B, when you say the highest power. On the other hand, when you say 3n plus 7 is something that's higher, and log n to the power of n or n squared, you're somehow misleading whoever is listening to your runtime. Even though that's correct, but it's just not accurate.
Okay.
So Rashid, does it make sense to you?
Yeah, okay,
Yeah.
that makes sense.
Yeah, the also in the extreme case, for example, let's say if you in your introductory Java course, you write system.out.println hello world. It's a very simple program there that should be the most accurate running time should be big O of 1. It's a constant time operation always. However, mathematically, I can say that one is exponential big O. It's still correct, but just not very useful, right?
Oh, okay.
Yeah. Okay.
And I just want, because I was basically kind of generating questions for myself to practice from AI.
Yeah.
I just wanted to clarify this.
Okay, sure.
We're not covering space complexity as a topic, right?
Space complexity, no, we are not. We are not.
Okay.
Yeah, that one I can tell you no. I think that the only, to be fair, I think the only time that we ever talk a little bit about memory space was if you remember in the very beginning of the asymptotic upper bound lecture, we kind of use some example to show to you, if you actually got like a string builder versus a string concatenation, right? Somehow the amount of space that's going to be taken in the slower algorithm is going to is going to make the algorithm very slow. I think that's the only example we did. But yeah, but for the exam, no, you don't need to worry about space complexity. No, only runtime. I mean, only time complexity. I think once you guys go to 3101, I think there might be more discussion about it. Yeah.
Okay. Yeah, just want to clarify that.
No worries. Yeah, guys, any other questions? You can feel free to speak up, or if you want to type on the chat, that's also fine. Yeah, take your time. I think I can pause a little bit, just in case you want to take some time to formulate your question. Also, there's another tip. It's not nothing to do with the contents, right? I think, well, for those of you who might be feeling comfortable writing in pencil, I think that could be some advantage for writing the paper exam, because you will be given some answer boxes for you to fill out the answer on the question sheet. So if you write in pen, if you're comfortable with it, if you don't make any mistake when you write out the answer, that might be fine. But if you constantly have to somehow revise your wordings, or you want to somehow make your font size a little bit smaller, etc., right? I think using pencil and eraser could be a little bit more efficient for the exam. You can consider that. Okay. But just please make sure you don't write in a red or maybe bright color, either black or blue, for the pen. Just make it so much easier for us to grade. And of course, naturally, since our written test a while ago only covered pretty much the very introductory part for the trees, right? So I think after the written test, we actually covered quite much about the trees. Like a binary tree, binary search tree, heaps, also many things about trees. So naturally, I think that might be the part you're less familiar with. So maybe in the coming few days, once you feel more once you hopefully it wouldn't take as much time, for you to revise what actually happened before the written test, so you can spend a little bit more time, studying for the trees. All right, let's see. So for question 3E, is the solution. Okay, good. So I think for this one here, I think for part E over here, that's pretty much all you got to provide. Yes, that's correct. That's what you got to provide. However, so you may want to go back to maybe what we cover in the lectures. You got to be very careful whenever you choose. Apparently, this one here, we are using the strategy that we spoke about in the class, right? It's going to be the sum of the absolute values of the multiplicative constant, right, for all the powers in of each term. And then if you add it up together, it's going to be 78. In this case, according to the little proof we did in the class, so this one is guaranteed to work. However, there might be some other cases where the upper bound effects may not necessarily begin when n0 is equal to 1. So you got to be very careful. So I would suggest, even though in this particular case, yes, it will be enough. If you just say, I will choose the C to be 78, and I'll choose n0 to be 1. Yes, that's enough. However, if the upper bound effects does not happen to start from n0 equals 1, then this answer here will be wrong, right? So you better always verify as part of your answer to say, okay, I choose this C here, I choose, and the n0 is equal to 1, and then I'm going to verify that as part of my work to show that the upper bound effects really start from there. If it doesn't, you may want to choose maybe n0 being equal to 2 or 3 and 4, etc. So that's something you got to watch out for. And question. Ammo deep, go ahead.
I have a question, the same question on the 3E. I was just wondering, like,
Yeah.
is there like an example where like n0 equals 1 will not work?
Will not work? Yeah, absolutely. So let me be more specific, because that's indeed something that we cover in the class, and I will definitely suggest you can go there and maybe take a look at that part. Okay, give me one moment. I'll show you, I'll show you which lecture you should really go to. I think, okay, it should be around 6 or 7, either way. Okay, but let's take a look at the slides. You can also go back to the iPad notes if you want to, right? But I'll show you where you can look at on the slides. Okay, it should be around here. Oh, by the way, so that's a little proof that I kind of mentioned earlier. So whenever you got like a polynomials only, you can just add up, right? That will be the C and N0 you choose, right? And then if we look at a little bit deeper, a little bit further, okay, for example here. Yeah, so this will be the example you can review. Let's say this one involves log, right? So this one here, if you simply choose C to be 5, as we show in the class, and also you can look at the argument here on the slides. If you choose C to be 5, so where does 5 come from? You simply add up the multiplicative constant here, 3 and 2. They're both positive, right? So we just adding up, 3 plus 2. So we got 5. However, in this case, N0 cannot be 1. Because as we try to argue over here, if you start with 1, the upper bound effects does not really start from N0 equals 1. So that's why you have to try maybe the next N0 value. Maybe try 1. If 1 doesn't work, you can try 2. If 2 doesn't work, you can try 3, and etc.
Okay.
Yeah. So maybe take a look at this example again. In case you want to review only just that part of the lecture, you can just go back to the recording. I think that part is actually quite important. Yeah.
Okay.
Yep, sure. Okay, Lawrence, go ahead.
It's on the same question.
Yeah.
3E.
Yeah.
So, are we supposed to find the tightest, like?
Okay, I see what you mean. Yes. I think, okay, if the question goes like this, to only say proof, right? So in that way, to really prove it, we just follow the definition for big O. You just gotta choose the C and N0. If you didn't follow the strategy that I showed to you, for example, if you didn't follow exactly this strategy over here by choosing the smallest possible C value, that's okay. As long as the C and N0 works, that'll be okay. However, if the question actually go a little bit further to say, prove that this, and then we might say there's a requirement there, you want to choose the smallest C possible. In that way, of course, you better just use that strategy. So it really depends. The question will be very explicit about what you should do.
Okay, thank you.
Okay, sounds good. All right. Yeah, if you got any other questions, feel free to post on the chat or speak up. Lawrence, again, go ahead.
Sorry, one more thing.
No worries.
So for 3E, if we were asked, we were asked to find like the closest starting point.
Yeah.
Would this one be 68 and not 78? Because of the -5 there?
You mean the smallest one, right?
Yeah. Because if we put n as 1 for this function here, it'll be 68.
I see what you mean. I see what you mean. It could be 68, yes. So, okay, let me see. In this case, if you actually choose, so we get when n0 equals 1, in that way we got 4 minus 5. Okay. Yeah, I think you're right. So again, so I think the question itself will be designed carefully. You're right. In this particular case, yes, if you actually choose the 4 minus 5 plus 59 plus 1 plus 9, in that way it's going to give you 68. In that way, yes, that'll be the smallest one because the upper bound effect will still be valid starting from n0 equals 1. So if the question asks you for the smallest C value, that'll be 68. Or the question can say, maybe use the proof strategy that we discussed in the class. In that way, you will have to choose the absolute value version. In that case, it's going to give you 78. Or if the question didn't specify which strategy you should really use, you can choose some arbitrary value as long as they work.
I see. Okay, thank you.
Okay, that's a good question. Yes. All right, guys, any other questions? Okay, Deep, go ahead.
I have a question. I'm just wondering that will there be like programming questions where like
You mean writing
you're
the
given
code?
like the yeah, you're given the
Uh-huh.
not like write the full code, but like you're given like the full code, but like there's some like missing lines in there, right?
That one is definitely possible. It's definitely possible. But I think the bottom line is a paper test. It's not really like a programming test. So you definitely wouldn't be expected to write something, like a, similar to this difficulty like a programming test. No, that one is for sure no. You could be asked to maybe trace some Java program, or it could be maybe to implement some small method, but definitely not as difficult as what we actually cover in the programming test. And like a missing line, that's also possible. Yes. Yeah.
Thank you.
Okay. No worries. Yeah, another tip I can also suggest, of course, data sheets, as I clarified earlier, data sheet is not allowed. However, it doesn't really stop you from maybe making a data sheet anyway by yourself, because by making it, the process of making it kind of lets you kind of concentrate about what information you don't feel as confident. You can put something on the data sheets, and that can kind of focus your review, maybe 1 or 2 hours, before the exam. So you can still look at the data sheets. Of course, you can use it in the exam, but I think that the process of preparing a data sheets could be very useful. You guys can also consider. Okay. Yeah, so of course the actual example question here, I think they are valuable. They definitely can cover certain aspect for the course, but there are many things that are not actually covered. So you guys gotta make sure you kind of review everything that we cover in the course. Okay. All right. Any other questions? Okay, I'll pause for one more moment, just in case you're still thinking about your questions. Lawrence, go ahead.
It's from the written test.
Sure. Which one?
It's where we were asked to find like it was x times something like an expression. And this one.
Mm-hmm.
So over there, the I less than n plus one.
Mm-hmm.
The answer was n plus two, I think.
Mm-hmm.
Could you explain how you got n plus two?
And plus 2 over here, let's see here, is I less than n plus 1 over here, right? Over here.
Yes.
Okay, so let me see this one here. And less than, okay, that was n plus 2. I would tend to think, let me just see over here. For each of the following part extracted from, choose the exact number. Okay, so we talk about an execution, okay, until termination. Okay, so you want to think about how many times this one here is executed over here. So that one there is going to be so this one here is actually number 5 over here. Okay, number 5. And j less than, oh sorry, were you asking about n plus 1 here, or maybe the
Yes,
n minus
number 2, the n plus one.
n plus 1 over here. Okay, Sure. That one there, let me see. Okay. You know what? This one could be some mistake on the answer itself. Okay, I just noticed that. Because if, okay, let's just get it right first. Okay, so here you can see that if you only look at this one here. So, let me just make a copy of it. Okay, right here. All right, good. Okay, let's if you only look at this part over here. Okay, so you want to think about how many times it's going to be evaluated. Okay, so I is going to be 0 in the beginning, and then it's going to be 1, and then 2, all the way to just n. Okay, when these are all the values where you're going to get the true value. And then when you eventually get to n plus 1, and that one there is going to give you the false value. Okay. So how many times are we evaluating that expression there? So we go from 0 all the way to n plus 1. So it would be n plus 2. Okay, that's n plus 2. However, each time we are evaluating this expression here, we're going to evaluate the less than comparison. Also, we're evaluating the plus, so 2. So it should be 2 times n plus 2. That should be the correct answer. Okay, so it should be 2n plus 4, or either way. So that one there, I wouldn't worry too much about it. It's definitely some maybe a few marks from the written test. I can try to maybe look at each one of you who actually got this, maybe chosen the correct answer, and then it might make a difference in the final grade. In that case, I can definitely consider it. Otherwise, it's a small portion. But it's more important to see this one over here. So the correct answer should be this.
Thank you.
Yep, good. Okay, Amaldeep, go ahead.
About the same question.
Yeah.
Can you explain again why is it n plus 2 again?
N plus 2, of course. I think for this one here, since we're talking about how many times we actually evaluate this expression over here. So if you think about the meaning of a for loop, so as long as this condition here is true, we are actually going to keep executing the body of the loop. So that means these are all the values of I that's going to make this expression true. So you can see when I is equal to 0 in the beginning, so 0 less than n plus 1, and also 1 less than n plus 1, all the way to what will be the last value of I that's actually going to make n plus 1 less than actually true. So it would be exactly 1 less, right? So it'd be all the way to n. So that means if this one here, that'll be n less than n plus 1. So that'll be the last possible value of I that's going to make this less than true. As soon as we increment another one to I, is going to be n plus 1. So now you got n plus 1 less than n plus 1. So this will be the first value that's going to make it false. As soon as it gets to false, then of course you exit from the loop. So now if you count how many times we're going to evaluate this expression here, so you go from 0 all the way to n, and then plus 1 more, right? So that's going to be n plus 2. That's how we got it.
Oh, I see.
Mm-hmm. So the pattern here is also similar because we're using the for loop, and the meaning of the for loop or while loop doesn't really change. So just the definition for any programming language. So you just gotta remember you're gonna get a bunch of maybe true values, so that's why you keep iterating through the body of the loop, and then you're gonna to ensure termination of the loop, you have to ultimately get to a value where the condition here is gonna evaluate to false only once. As soon as you get to false, then you don't evaluate anymore. You don't iterate through anymore. Yeah.
Okay.
Yeah. Yeah, I think the primitive counting exercises that we have been doing in this course, that's just another way to somehow review what you did maybe in 1021 or 1022. Back in the first Java course, maybe you already started writing some for loop or nested for loop. So now we just try to be more precise about what's happening over there, right? That's also a nice way to really study a little bit deeper into the code structure. All right, any other questions? All right, I'll pause one more moment just to see. Yeah, Lorenz, go ahead.
I think I don't know if you mentioned it, lectures, but I just wanted to clarify that
Mm-hmm.
for a singleton node, like a root node,
Yeah.
would it be considered a complete binary tree?
That one I don't think I mentioned explicitly. Okay, so you're basically saying if we got a singleton tree, okay, if you got a singleton tree and then you just got a single root, you're asking whether this should be complete, right? I think it would be, because in this way, the height is actually equal to the height would just be 0. So this is like a boundary case over here, right? So we didn't talk about this explicitly. So I think at this one, yes, it would be. Because if you review all the different conditions over there, somehow they would just not be applicable. Because here we talk about h minus 1, h minus 2, but the thing is h is only 0, right? So this one kind of go back to the like a boundary case where whenever you got for all quantifier, and then if the range is actually empty, and then you get true automatically. It's a little bit like that scenario. So this singleton tree will be both complete and full. And to see that it's actually full is actually a little bit easier, because you can think about just for this level here, if I only got one level, at level 0, the maximum number of nodes will be 2 to the power 0, which is 1, and I already got it. So that's guaranteed to be full. And we know that full binary tree implies it's actually complete binary tree. Yes.
Okay, thank you.
Good. All right, any other questions? Yeah, Amaldeep, go ahead.
Hello. When you mentioned that the data sheets won't be like available for the allowed for the test, like,
Yeah.
do you think that data sheets are kind of like another way of saying sheets, right?
Yeah, well, yeah, no, yeah. People like to call it cheat sheets, but I just don't. I just personally don't call it cheat sheets. Data sheets, or I think some people call it creep sheets. I just call it data sheets. So the point is, you are not allowed to use any data sheets, or it's a closed book exam, right? So you're not allowed to use any study guide or study aid. So I'm just saying that by preparing a study like data sheets before the exam can also be useful for your study, because that somehow force you to focus or concentrate on what's really something you kind of don't feel as confident. You can put it on the sheets, and once you get the sheets completed before the exam, let's say maybe about 1 hour or 2 hours before the exam, if you want to do some last minute study, you can look at the sheets you have prepared. That could be a nice way. Yeah.
Okay. Thank you.
Yeah. All right, so guys, if you have no further questions, shall we call it a day? All right. All right, thank you for coming. And then good luck to your exam on Sunday. I'll be there. And then I will make some announcement when we get a little bit closer to the exam, just to remind you some details about the exam day, right? So I'll reach out. Okay. All right, thank you so much. And then I'll see you guys soon. Bye-bye.
Thank you, sir.
You're welcome.